Now let's look at the second way of implementing generic operators, right? And we call this way data redirected programming. Before we start, let me just warn you that this is going to be a little bit complicated. Pay attention and let's see how far we can get. Alright, so the idea is actually to use what we call a table lookup, right? So essentially we have a table and we figure out how to match the function to the data type from looking at the table. So the idea here is that when you have a generic operator, the operator will look at the tag on the data, right? And then the correct operation that is required to be applied on the data is found from this table, okay? And this method also addresses the problem of naming conflicts, okay? And it allows us to add new types easily. What you do is just add more entries to the table. All right, so let's take a look at this chart, okay? So the idea here is that, okay, there are 4 operations. There's real part, imaginary part, magnitude and angle, right? And there are 2 kinds of data representation, the polar and the rectangular. So each of them have their own like real part, imaginary part, magnitude, angle functions, right? And the idea here is it's okay, you don't have to care about the names, right? You put them into this table, and every time if you want this operation, for example, real part, you will check the data, right, and go and pick out the function that you need from this table. Okay. Now, so before we start, let's talk about some functions that we need to understand to manipulate the table. So essentially, the table supports 2 different operations. You can either put, right? So you can put op and type, okay? And item is actually the function, right? The function that you need to use to operate, okay? And you can get, okay, op and type. So what you can put in the table for op and type, you can also extract using get. Okay, so it's put and get. Now, before we continue, let me just briefly talk about this new data structure called a dictionary, okay? So sometimes it's convenient to have a data structure that allows us to do this retrieval by keyword and output and get, right? So typically, we have this kinds of data structures called associative arrays. Okay, so Python dictionary is an associative array, okay? And basically, if you remember, the tuples use the round brackets, right? Okay, the lists use this square brackets. All right, dictionaries, they will use this curly brackets. Let's take a look. So the way a dictionary is structured is the following form. It's actually key value pairs. So it's key 1 and value 1, comma. Okay, key 2, value 1, 2, comma. So it's just a bunch of key value pairs. And this 2 curly braces is empty dictionary. For example, you can have whether equals to this thing, right? This is actually equivalent to dictionary. Okay, you can use DICT to convert dictionary. And basically, you have this key value thing. So temp is equal to this, win is equal to this, des is equal to this. All right, so this converts this into a dictionary. Let's take a look. You can also use a list of pairs. Okay, so this is a list. Okay, these pairs are actually tuples. And you can use DICT to convert them into a dictionary. So 1, 2, and 3 are keywords. Okay, and these are the values. Okay, similarly, you can do this. Okay, and then you can access the value using the key. So temp here is a key. So if you use this thing, square brackets, the key, you will get the value associated with the key, which is this thing. So it turns out that the value associated with temp is actually another dictionary. This is a dictionary. Okay. And yep, so if you do whether some key which doesn't exist, okay, then you get a key error. You can also do things like win in whether. Okay, if you look at this dictionary, whether has win inside as a key, so win in whether will be true. Okay, 0 in whether false. Okay, now next thing, if you do whether is nice equals true. Okay, this is actually an assignment sort of thing, right? So essentially you add another dictionary entry to the dictionary. So you can also do del whether temp. Okay, this deletes an entry from a dictionary. And now if you list whether.keys, whether.keys gives you all the keys in the dictionary. And what happens is that is nice is now a key, right? And temp is no longer a key, has been deleted. Okay, and if you do whether.values, you get the list of all the values. Okay. Now it turns out you can also do this looping constructing, whereby you can do for key in whether, Okay, and then you can just print weather key, and then you get all the keys. You can do for key comma value in weather.items, right? And you can print key value, you get this items. Okay, and you can clear the dictionary and clear everything inside. So given this, right, the natural way to implement a table that we need to use the dictionary. Let's take a look. First, look at put. To put something, an op types in the prop. To put a prop, okay, index with op and type. Okay, we check whether op is in the procs. Okay, procs is actually the dictionary of dictionaries, right? Now, if it's not inside, then we create a new dictionary for op. Okay, it's empty. Okay, and what we do now is that this thing is now created, right? So we will just basically add prop, okay, to the prop dictionary using types as a key. Okay, so this is what we also call a 2D array. All right, now let's take a look at what the table looks like. Okay, so this table is called procs. It has got 4 different operations. Okay, there's a real part, imaginary part, magnitude, and angle. These are function names, okay, of the functions you want to call for the various generic operators. Okay, and next, each of them, right, the value associated is some kind of a dictionary, right, and this dictionary basically is keyed by representation. So there's a rectangular and there's a polar, and associated with each of these keys is actually the function that will operate on the different data types, okay, to extract the real parts. Okay, let's take a look at how we will install Ben's package. So Ben's package, remember, is the one that deals with the rectangular coordinates, right? So it's actually, we call this function to install the package, install rectangular package, okay? Now, basically, it defines a whole bunch of these operations. These are what you saw earlier. So it is make from real, imaginary, real part, imaginary part and so forth, right? Now, the more interesting thing is on the second page, right? So basically, it's a tag thing. There's a tag operation to add a tag to different data types now. And the more important part is this parts, okay, or the installation of the operations. So basically, real part, imaginary part, magnitude, angle, make from real, imaginary, make from magnitude, angle. All these 6 functions were defined in the previous page, right? So the code has been executed, and these 6 functions have been created already. Now, what we do here is that we basically put these functions, the 6 functions, into the table, okay, and we index them by this function name as well as the data type. Okay. Now, similarly, Alyssa's polar package. Okay, these are the definitions for the polar package. This one you saw actually in the last lecture. Okay, and again, we install this into the table. So there's a tag function to tag the data. All right. But more importantly, all these statements here to put, okay, the 6 functions that you saw in the previous page, right, and index them using the function name and the type. Okay, now the important thing to realize here is that with this new technique, no longer have any name conflicts, right? If you look at how the Lissa's package and Ben's package were defined, they all use the same function names, right? But it's okay because the function names are all actually local functions within the installers. So this technique allows programmers to use identical names and hide them, okay? In other words, the names are now live in separate namespaces, okay? The installer defines all the operators and places them in the table according to the operation and type, right? So you don't ever actually need to access them by name, okay? But you still need tags to distinguish between the types. All right, so now let's take a look at how we will actually go and use this table to implement our generic operators. So the 2 functions that we need to look at, one is called apply generic, okay? And so this apply generic we'll call type tags, okay? But let's take a look. So first of all, you try to apply an operation, right, to a bunch of arguments, right? So you're trying to do something, right? And what you do then is that you map the type tag, okay, on arguments. Now what does this do? This type tag, okay, when applied to each element in the arguments, right, it checks whether it's the tuple, so it means it's a valid data object. It checks whether the length is 3, and if so, it returns you the datum 0. This, remember, is actually the data tag, right? So here, this returns you a tuple of the tags for the various argument types, okay? And what you do is that you go to the function table with all the functions and you get right? The function for the op, okay, that will be applied to these types of data, right? And then this gives you the function, okay, and you apply the function onto the arguments. Now, interestingly, there's this star thing here, and we talk about that. The star notation allows you to take care of functions with variable number of arguments. For example, if you do define f, x, y, star, z, or z, right, and this body. So this function f can be called with 2 or more arguments. Now, if you call function f with 1, 2, 3, 4, 5, 6, right, then 1 gets mapped to x, 2 gets mapped to y, and everything else here, okay, is put in a tuple and gets mapped to the z. Okay, that's what it means. So star means that I'll take whatever is coming after. Now, so let's take a look at how this works. Now, if you call op with a star args, right, that means it will basically map whatever number of args onto the function. Okay, so let's take a look. So suppose we do funky op, right, and we do funky op lambda x squared 2. Okay, so 2 is the args, and then lambda x squared is actually the op, right? So now when this happens here is that 2 is applied to x. Okay, and later on if you do lambda xy, x plus y, then 2 becomes x, and 2 becomes x, and 1 becomes y. Okay, so you get 4 and you get 3. Right, let's take a look at how you actually do the general operators. So let's say you want to do real part z. Okay, then what happens is that you just basically use apply generate real part and z. Okay, imaginary part you just apply generate imaginary part and z. Okay, so forth. Okay, now what happens, okay, is that the apply generate, right, will retrieve the appropriate function or prop from the table based on op and type, right? Then applies prop to the arguments. This style of programming, as I mentioned, is called data-directed programming. Now let's think of some issues. So why would you want to do this data-directed programming rather than the earlier one, which is dispatch on type? Think about what happens when you need to add a new type operation. What kind of code changes need to be done? Right? Are there any naming conflicts? Okay. And the question is, who should maintain this table? Right. So these are the questions that we will discuss in class. Also come for our station next week.